Hi everyone. Today let's talk about section 8.4, the divergence and integral test. Big idea. We can determine whether some series diverges or converges by comparing the series to another series with no convergence or divergence, or by thinking of the series as a Riemann sum and compare the area to known integrals that converge or diverge. Big skills. You should be able to determine the convergence or divergence of certain series using the integral and comparison test. Okay, so here let's look at some properties of series. Okay, so suppose the series a sub k converges to a, and let c be a real number, then the series sum of c times a sub k also converges. And we know the property of the sum. We can put the constant multiple in front. So that's why this series also converges to c times a. Okay. And suppose the series converge to A and the series BK converge to B, then the series of their sum and difference actually converges. And that's because of the property of the sum. You can choose to sum this guy first and then sum this guy and then add them together. Okay? And whether a series converges does not depend on a finite number of terms added to or removed from the series. For example, this two series, so this is a series where the terms is AK, so K is from 1, okay? So this is like A1 plus A2, the terms start with the first term, okay? And then the second series, well, we start with the mth term, okay? So actually those two series both converge or both diverge. Actually the problem make it diverge is about the tail, okay? Is what happened when k goes to infinity, okay? So adding a finite number of terms or subtract a finite number of terms will not change the convergence, but however, if they converge, that will change the number which they converge to. Okay, yeah, so that's why the value of convergence series does change if non-zero terms are added or deleted. But if both series are diverges, then the other ones is just going to be diverges as well if we just add some finite number of terms. Okay, so here we have the divergence test. If the limit of the sequence does not exist, or the limit of the sequence exists but not equal to 0, then the series diverges. So here we have two concepts. The first concept is the sequence converges or diverges. Okay, so sequence converges, it means the limit of a sub k when k goes to infinity is a number. The sequence diverges means the limit of a sub k when k goes to infinity, this guy does not exist. It might be it goes to infinity or minus infinity, or it might be the sequence like oscillating between two numbers, like a 1 minus 1, 1 minus 1, 1 minus 1. Then the limit does not exist. So that's about the sequence. How about the series? Okay, so series, we also can talk about whether it converges or diverges. What does that mean by saying series converges? Series converges means the sum of k from 0 to infinity, a sub k, is a finite number. Okay, so this sum is so the limit of a sub k is just like what happened at the end, at the tail. Okay, the sum, it really is like the sum of all the a sub k. So that is like a stronger property of that. Okay, and diverges means the sum Okay, this guy, the limit does not exist. And how do we say the limit does not exist? If you can remember, when we define it, we can define this guy is the limit of the nth partial sum, okay? Where Sn is the sum of a1, a2, up to ak. A sub n. Okay. So that's why here, if the limits of a sub k does not exist, so for example, if we have the series like that, you're adding infinitely many values, right? If the tail, the limit does not exist, well, of course, when you add them up, then the sum has no limits, okay? And even though if the limits of the sequence exists but not equal to 0, think about it. If let's say the limit is 1, well then what happened? You're just adding for the sum, for the series, you're just adding bunch of 1. So that's why the series also diverges. So as long as the sequence diverges or the sequence converges to a non-zero number, then the series will diverges. Okay, so equivalently, okay, we have the contrapositive statement. If the series converges, okay, when you add them up, then your tail has to be 0. So when you add up all this guy together, it's finite, then your tail may better be 0, because otherwise you're adding infinitely many positive big numbers, so the answer won't be 0. Okay, second, if the limit of a sub k is 0, then the series may either converges or diverges. Okay, so if the tail goes to 0, it doesn't mean that the series must converge. Okay, it still might be converge or diverge. So that's why for the divergence test, it can only tell when it diverges. Okay, it doesn't tell when it converges. Okay, so from now on, when we ask you to find determine whether the series converges or diverges, the first step is to compute the limit of the sequence. Okay, if the limit of sequence is not 0, then we know the series diverges. That is by the divergence test. Okay, if the limit of the sequence is 0, then the divergence test is inconclusive. We need to use other tests to figure that out. Okay, so in this chapter, we'll learn a lot of tests. And at the end of the chapter, I will make a summary and comparison among the tests, so you can see when to use certain tests and what's special about those series. Okay, so let's look at example 1. Evaluate the infinite series. Okay, so first of all, let's look at this guy. So we can use the properties of the series. We can split. So we have k equals 1 to infinity. And we have the 5 here, 2 over 3, and then the k. And we can use it to subtract sum of the series. Okay, so what is this guy? Well, minus 1 is like we have a 1/2 there, right? And then 2 to the k over 7 to the k. What is that? Okay, so you can see each of them is actually a geometric series. So for a geometric series, we have the formula. Okay, so the first one, we have this guy and 2 over 3 to the k. The second one, we have 1/2 is the constant. Then we have 2 over 7 to the k. Okay, so let's look at the first one. This is the r. Because r is less than 1, Okay, this guy converges. So this guy converges to what? First term, what's the first term? Well, first term is when k equals to 1. So we have 5 times 2 over 3. 1 minus r. R is 2 over 3. So we get 5, 2 over 3 over 1 over 3. 3 cancel. We have 10. Okay, that's the first series. The second series, we also have the r is less than 1. So we know it converges, but it converges to what? So it converges to the first term. What is the first term? That is when the k equals to 1. And then 1 minus the ratio. So 2 cancel 1 over 7 over 5 over 7. So we have 1 over 5. So that is why by the properties of series, we have this guy is 10 minus the second series is 1/5. So it's like 50 over 5 minus 1, 49 over 5. Okay, so that is first page. Let's continue. Okay, so this one, you can see we can actually split, and this we can split the first one, and we can actually put the 5 in front, right? So we have 1 k times k plus 1 in the denominator, and then we have 2 over 3 to the k. Well, if you can remember, last time we calculated this. This is a telescoping series, right? And 1 over k times k plus 1 is actually 1 over k minus 1 over k plus 1. So this is like 8k. And what we did is Sn is then a1 plus a2 plus ... an, we get 1 over case 1 minus 1 over 2 plus 1 over 2 minus 1 over 3 plus this is 1 over n minus 1 over n plus 1. So all these terms cancel and the bigger index arrive. So S infinity is the limit and goes to infinity 1 minus 1 over n plus 1, so we get 1. Okay, so this series, not include the 5, equals to 1. Okay, so that's why we get 5 times 1 minus k from 1 to infinity 2. Well, this is like what? 1 over 3 to the k. Well, this is our r less than 1. So this is a geometric series. So it converges to first term. K, we plug in k equals to 1. So 2 times 1/3 minus, so over 1 minus 1/3. Well, that's 2/3 over 2/3. They cancel, we get 1. Wow. So what is our answer? Let me see. Okay, so our answer is our answer is 5 times 1 is 5 minus 1. So that is 4. Okay, so this is our answer. So these problems, we use properties of the series, okay? And we also use the concept we learned from last sessions, the geometric series and the telescoping series. Okay, so for the next problem, let's look at example 2. Okay, so for the remaining series, we're gonna try to use the divergence test. Okay, so what is divergence test? Well, you figure out that is AK. Okay, and then we want to compute the limit k goes to infinity. Okay, when k goes to infinity, what is limits of a, k. Alright, so when k goes to infinity, we look at the dominant terms. Remember? We look at the dominant terms. So here, this is the dominant term. This is the dominant term. So dominant term of numerator is 15k cubed. And dominant term of the denominator is square root of 4x to 6. Square root of 4 is 2. Square root of x to the 6 is actually 3. Right? So that's why here we get that is the limit 15k cubed over 2. Oh, so sorry, this is k, this is k. We don't have x. They are k. So k cubed and k cubed cancel. So we have 15 over 2. So if we get the limit is not 0, then what do you say? We say series diverges by divergence test. Okay, so this is how we solve the problem. Let's continue. Okay, so the first step, we compute limits k goes to infinity of a sub k. Well, what's a sub k? What is the degree of the numerator? It's like square root of k squared. So dominant term of numerator is square root of 9k squared. So square root of 9 is 3. Square root of k is k because we're assuming k is positive. Okay, and dominant term of denominator, you can see here we have the degree 1 term, but here actually this is also a degree 1 term. So it's 13k plus square root of 64k squared. That's 13k plus square root of 64 is 8. So what's 13 plus 8? 21k. So that's why we have limits k goes to infinity of 3k over 21k. They cancel, we get 1 over 7. So in the exams, make sure you include this. Okay, so write this, okay, in the exam. It's so important. Okay, and because 1 over 7 is not 0, as long as the limit of the sequence is not 0, then we have the series diverges by divergence test. So in this chapter, we will learn a lot of tests. So every time when you use a test, you have to say its name. Okay? Yeah, so I really hope that there are two concepts you're gonna distinguish: the series and the sequence. So in these examples, you can see the sequence converges to a number, but because that number is not 0, so the series diverges. Sequence converges, but series diverges. Okay? Alright, let's continue. Okay, so let's see here. First steps, limit of k goes to infinity of a sub k. So this is a sub k. Alright, so also gotta be careful because sometimes when I grade students homework or exam solutions, I see students do something like this. No, that there's no such notation. Don't combine them together. It's either limits of the sequence or the series. Okay, don't combine those together. So limit of the sequence, not the series. Don't put the sum over here. So limit of the sequence, what is that? Well, we look at the dominant terms. What is the dominant term? Is the power function dominant or the exponential function dominant? It has the exponential dominant. So dominant term of numerator is 3 to the k. Dominant term of denominator is 2 to the k. So that's why here we get limit 3 to the k over 2 to the k. What is that? Well, we can combine them together. So you don't just plug in infinity here. You get infinity over infinity. Oh, what's that? Well, you actually combine them. Now, let's look at the base. What happened with the base? The base is greater than 1. So remember, if the base is greater than 1, my exponential function is actually increasing. If my base is less than 1 but greater than 0, my exponential function is decreasing. So in this case, we have the increasing picture. So when k goes to infinity, this guy just goes to infinity, blows up. Okay? Alright, so that's why, because the limits is not 0, we have the series diverges by divergence theorem. Okay? Alright. See? Okay, let me ask you more questions. Okay, so more questions. So what if, well, instead of that, we have like 7k to the 45 plus 2 to the k instead of 3 of k. What if the position of 3 to the k and 2 to the k change? Well, if we have this, you notice that the limit k goes to infinity of, let's call this guy is b sub k. I don't want to call them a sub k because they're not this. I don't want to confuse with this guy. Okay. And by the way, here, don't put equal. They're not equal. The left hand side is the series. The right hand side is the limits of the sequence. They're not equal. So you just put a comma there. They're not equal. Okay? Well, you can see here, now we get the dominant term of the numerator is 2 to the k. The dominant term of the denominator is 3 to the k. So we have 2 over 3 to the k. Well, this is this picture. So you can see when x goes to infinity is actually 0. If you get 0, what happened? If you get 0 means there is a, so this is step 1. If you get 0 means there is a step 2. Use other test. Okay, which we're gonna learn in the remaining chapter. Okay, but if it's 0, don't say it converges. Okay, that divergence test only tell us when it diverges. It won't tell us when it converges. Okay, so you only know that it diverges, but if this guy is 0, it may diverge, it might converge. We don't know. Divergence test doesn't tell us anything about that. Okay? So be careful. So if this is 0, the divergence test is inconclusive. Okay? So we need to use other test. Okay. So that is the first test we learned, the divergence test. Next, let's talk about integral test. So what is integral test? Suppose f is a continuous, positive, and decreasing. Okay, so we have 3 conditions need to satisfy. Continuous, positive, and decreasing function for x greater or equal to 1. Okay, let a sub k is f of k for k in the natural number. Then the series and the integral either both converge or both diverge. Okay, so in this case, the value of the integral is not in general equals to the value of the series. Okay, so how do we show that? Let me get more space here so I can give you some idea why this works. Okay, so Let me get more space here. Okay, so let me see. How do I get more space? Let me do enter. Okay. Okay. All right. Let me draw some picture. So first of all, I would like to draw. Okay, so draw right here. I would like to draw this picture. Okay, so draw another picture. Oops. So this is f of x, this is f of x. Okay, you can see it's continuous, positive, and decreasing for x greater or equal to 1. Let's say 1 is right here. Okay. All right, so I want to compare this guy. So the integral, what's the integral? Well, this integral is just like the black area, right? The integral is the area under the curve from 1 to infinity. So this is improper integral. Okay, now next, I'm gonna draw some pictures. So first of all, let's look at this one. So let's say this is 2, this is 3, this is 4, this is 5, etc. Okay, all right, let's figure out what is this. Wow. Okay, so what is this height? Well, this is like you plugging 1 into f. So f of 1 is actually a sub 1. Okay, so then what is this area? Well, that's a sub 1 times 1. See, the length of this interval from 1 to 2 is 1. Next, what is this guy? This is a sub 2, so the area is actually a sub 2. Then this is a sub 3. And this is a sub 4, right? The area. So what is the area? What's the orange area? So the orange area is actually sum a k from 1 to infinity, right? And can you see the orange area actually bigger than the black area? Can you see? Yeah, so we have the orange area is bigger than the black area. And what is the black area? So orange area is greater than the black area. The black area is the integral from 1 to infinity f of x dx. So that's the first picture. How about the second picture? The second picture, let me choose a color. Let's see, do you like green? Okay, so I'm gonna draw it like this. So this is 2, 3, 4, 5. Okay. So what is this guy? Okay, so what is this guy? Well, this guy is actually a of 2, so a2, okay, f of 2, and this guy is f of 1, so a1, and then this guy is a3, this is a4 and a5. So far so good, everybody? Okay, so can you see what is the green area? So the green area, I didn't include this piece, okay? So the green, what's the green area? So the green area is equals to sum a k, but k start with 2. Yes, and what can you tell about the black area and the green area? the black area is bigger than the green area. Okay, now can you see the black, the integral from 1 to infinity of f of x dx is actually bounded between the two series, but the left hand side is the series start with a1, this series k start with 2, right? Okay, keep this in mind. Do you still remember we learned comparison test last time, right? So comparison test is like, oh, we have the big guy, if big guy converge, and then the small guy also converge. If the small guy diverge, then the big guy also diverge. Okay, so let's do it here. Okay, so if we look at this picture, okay, let me use different color. So from this inequality, we know that this is the big guy, this is the small guy, right? If the big guy converge, so if this guy converge, the big guy is finite, it implies the integral also converges, so the small guy is also finite, right? And we know that integral 1 to infinity f of x dx diverges. So if the small guy diverges, that implies the big guy also diverges. Okay? Alright, and how about the second picture? Well, the second picture tells us that, so from this inequality sign, we know this is the small guy, and now this is the big guy. So if big guy converge, that implies the sum k from 2 to infinity a sub k converges. This is the small guy. But remember, whether or not a series converge only depends on the tail. Does not depend on what it start with. So this is the same as saying the series k from 1 to infinity a sub k also converges. Okay, and if the small guy diverges, it implies the big guy also diverges. But remember, a series diverges or not, a series diverges or converges or not does not depend on the, did I press something? Okay, let's go back. Yes, it does not depend on the finite number terms. Okay, it actually depends on the tail. So this is the same as saying k from 1 to infinity of a sub k diverges. Now you see, if the integral diverges, the series diverges. If the integral converges, the series converges. If the series converges, the integral converges. If the series diverges, then the integral diverges. So they both converge or both diverge. Okay? So when do we use the integral test? We usually use integral test when our function, when our series is comparable to a p series. Okay, so p test. We have the p test for proper integrals. Okay. So if you can remember, we learned this in session 7.7 improper integral. Okay, the integral from 1 to infinity of 1 over x to the p is convergence if p greater than 1. Okay, and it converges to 1 over p minus 1. and the integral divergence if p less than or equal to 1. Okay, so this is what we learned in session 7.7. Okay, but now because we have this integral test, okay, then we know more information about this guy. So this guy is called a P series. Okay, so the P series, now we know it converges if P greater than 1, and it diverges when P less than or equal to 1. However, when it converges, it does not converge to 1 over p minus 1, because we just know the integral and the series both converge or both diverge, but we don't know what value it converges to. Okay, they don't converge to the same value. Like the previous example, you can see that the area are not the same. They're just like either both finite, both infinite, but when it's finite, then the area might be different. Okay, finite area, it could be 1, it could be 2, it could be 5. Okay, it is not necessarily the same. So we mark in the integral test, first, f does not need to be always decreasing. It just has to be decreasing for x larger than some number n. Okay. So if I draw the picture, okay, so the picture is like, you can have your function like this, but just at the tail, we make sure at the tail the function is continuous, positive, and decreasing at the tail. Okay, maybe in the first couple of terms it increase, okay, but the tail, it really matters. The tail determines whether the series or the integrals converges or diverges. Second, the limit of integration does not have to be 1. So we can integrate the integral from 5 to infinity. So that's why the first couple terms don't really affect whether the integral will converge or diverge. It's the tail matters a lot. Okay. All right. So let's see how we use the integral test to determine whether the following series converges or diverges. Okay. So first of all, define. First of all, I would start with compute the limits of the sequence. Okay. That's always the case. Okay, first let's compute limits of the sequence. So what's the limit of the sequence? Well, we look at the dominant terms. So here, dominant term of numerator is k to the 4. Dominant term of denominator is 2k to the 5th to the 3/2. What is that? Well, here we can see 2 to the 3/2, and then k, 5 times 3/2 is 15 over 2. All right, so that equals to limit. That equals to limit. K goes to infinity. Then we have k to the 4 over 2 to the 3/2, k to the 15 over 2. Let's simplify. So we have 2 to the 3/2 at the bottom. Okay, k to the 4th and k to the 15 over 2. Which one is bigger? Well, 4 is like 8 over 2, right? So the bottom is bigger. So 15 over 2 minus 4 is like 15 over 2 minus 8 over 2, the 7 over 2. And you can see the numerator is just 1. The denominator is a power function of k. When k goes to infinity, this guy is 0. So that's why we have to go to step 2. We cannot use the divergence test. Okay? If this guy is not 0, then we can say by divergence test, the series diverges. Then we are done. But here, no. We have to continue. And if you can look at the series, do you notice that like the numerator we have k to the fourth? K to the fourth is sort of like the derivative of k to the fifth. Okay, so we can integrate this function by u substitution. So here's the complete steps. So we know we're gonna use integral test. So to use integral test, first you need to define the function. Well, this means whenever you see k, replace k by x. All right. And you can see the function is continuous, positive, and decreasing. So in the exam, you have, whenever you use integral test, you have to make sure you verify the hypothesis. The hypothesis we require f to be continuous, positive, and decreasing. Okay. And it is decreasing because you can see the denominator is going to be bigger, so eventually it will be decreasing. Okay, and all the terms are positive for x greater equal to 3. Okay, and so what's next? Next we want to compute the integral. So let's compute the integral from 3 to infinity. Alright, so we use u substitution. So let u be, so this is my u. Then du is what? Du is 2 times 5 is 10. X to the 4th dx. Then x to the 4th dx is 1 over 10 du. So this guy is what? So x to the 4th dx is 1 over 10 du. And then we have u to the 3 over 2. And then, so those 3 and those infinity, they are x values. So you either put u of 3 or u of infinity, and for that. Okay, so let's see here. Oh, we have another problem because infinity is an improper integral. We cannot say equals infinity. Okay, we say t, and then we say we are letting t goes to infinity. That's the improper integral. We cannot equal to infinity, right? We can only approaching it to get closer to infinity. Okay. So next, so that's limits t goes to infinity of 1 over 10. This is x is 3, x is t, and here this is like u to the negative 3/2 du. What is that? We add 1 to the exponent, so become u to the minus 1/2 divided by minus 1/2. Evaluate from x is 3 to x is t. Okay. So here you can see 2 and 5 cancel. 2 and 10 cancel. We get 5. So we have the limits t goes to infinity minus 1 over 5. And then here we have u to the negative 1/2 means we have the square of u in the denominator. Okay, so evaluate from x is 3 to x equals to t. Almost there. We want to get the x back because those are x values. So x is, so u is 2x to the 5th minus 5. Right? Okay, so now we evaluate from 3 to t. So we plug in t first. We plug in t 1 over 5. And then this is 2t to the 5th minus 5. Okay, and then subtract, negative become plus. We're plugging 3. We're plugging 3. Okay, what is 3 to the 5th? Let's see, 2 times 3 to the 5th, and then minus 5. That equals 481. Okay, and when t goes to infinity, you can see this guy goes to 0. So our answer is 1 over 5 square root of 481. Okay, so we get a finite number. It means the integral what? So the integral converges. Oops. Okay, okay, so how do I say? Okay. Okay, so because the integral converges, then we say, let me emphasize, then we say by integral test, okay, our series, oops, where is our series? Did I press some button? Okay, so our series, oops, then, oh, our series, okay. All right. So our series, okay. So we can just say series because there's only one series in this problem. So series also converges. Okay. And that's the problem. Let me see. Am I able to move this on the top? Okay. Okay, I can do it later. Okay. So that is part A. How about part okay. How about part B? Okay, so for part B, you can see, wow, if we let this be u, this is exactly du. So this looks like a function we're able to integrate. So usually if you see a series and it looks like an integral that you're able to integrate, then think about integral test. Okay, but the first step is to we find the limits. Okay, the limits k goes to infinity of e to the k plus 1 to the 4/5. Okay, let's see what happened. So actually here you can see the dominant term of numerator is e to the k and dominant term of denominator is e to the k to the 4/5. Well, we get k goes to infinity and then we have e to the k over e to the k to the 4/5. What is that? Well, which one is bigger? Can you see that is the numerator? The numerator is bigger. So we actually get e to the k and then we have 1 minus 4/5, which is 1/5. Okay. Well, what does that mean? So this is the same as e to the k over 5. Wow. E is greater than 1, so we have an increasing exponential function. When k goes to infinity, well, this guy goes to infinity. So we know, if this is not 0, then we can say diverges by divergence test. And we can stop right here. okay, for this problem, because we already conclude it diverges by divergence test. Okay, so let me change the problem a little bit to make it more interesting. Okay, so let me change the problem a little bit. So let me call this C, and then I call this D, and then I call, where is this? I call this E. Okay, so now what happened? Okay, so I'm gonna change this guy to 7. Okay, if I change this guy to 7, now what happened? Well, first up, you still want to compute limits k goes infinity of this guy, because it's very similar to the last problem. So let's just do it quickly. And you can see we look at the dominant term is e to the k. This is e to the 7 over 5k, and that equals to 1 over, because the denominator is bigger, so it actually becomes 2 over 5k. And we know that when k goes to infinity, well, this guy, the denominator goes to infinity, so 1 over infinity is like 0. So this guy is like 0. Okay, so in this case, divergence test tells us nothing, right? So we need to go to step 2. Well, step 2 is then we can use the integral test to compute. So to use integral test, first we gotta define the function in terms of x. Okay, and do you remember the 3 conditions we want to say? This guy is continuous, positive, and decreasing. And it's continuous, and it's positive, right? And it's decreasing because the denominator is bigger eventually. Okay? Okay, so yeah, so look at the picture. If it's positive and it's getting close to 0, so it's eventually gonna be decreasing. Okay, so now let's compute the integral from 1 to infinity, because k start with 1, so our integral also start with 1. And then e to the x over e to the x plus 7 to 5 over 7 over 5 dx. Okay, and in proper integral, we place infinity by t, then e to the x plus 7 over 5 dx. Okay, so you can see this problem, we use u substitution, let this be u, and then this guy is du. Okay, so this guy is like integral of u to the minus 7/5 du. Okay, so what is that? Okay, let's continue. All right, so we have integral of u to the negative 7 over 5. We add 1 to it. It becomes u to the it become like u to the negative. What? When you add 1 to it, what do you get? 2 over 5, right? And then we evaluate from x is 1, x is t. Okay, so yeah, you add 1 to the exponent, you also divide it by the new exponent, so you divide it by negative 2, and you times 5. So far, so good, everybody? So we continue to plug in. We plug in x, so this is minus 5 over 2. U is, so this is negative exponents, means it lives in the denominator, so we have 2 over 5 here. And then evaluate from, so now we get the x, we don't need to put x anymore. Okay. From 1 to t. Okay, so from 1 to t, we plug in t first. So we plug in t first, we get minus 5 over 2. E to the t plus 7 and 2/5. Minus negative become plus. We plug in 1, so we get e plus 7 to the 2/5. Okay, when t goes to infinity, because this guy, our denominator goes to infinity, this guy goes to 0. Yay! So our answer is 5 over 2 times e plus 7 to the 2/5. And it is a finite number. Okay, so if we get the integral, the improper integral is a finite number, we say it converges. Okay, so what do you say by integral test? Okay, so by integral test, our series also converges. Okay, so that is the solution of part C. You can see part B and part C, I changed a little bit, and the amount of work are quite different. Okay, part C requires much more. All right, part D. We have the sum k equals to 1, and then the series ln of k over k. So do you realize that the derivative of ln of k is 1 over k? So I see some u substitution there. So this function can be integrate. Then you can think about integral test. Okay, so here I also provide the graph of it. Okay, so but remember, let's stick with our steps. The first step, you always compute the limits of the sequence. So limit of the sequence, do you remember that ln of k and k, which one goes to infinity faster? Natural log function and k, which one goes to infinity faster? If you can remember what we talked about in the sessions 8.2, we say ln of k is the slowest. And then we have the polynomial or power function, then we have the exponential function, and then we have k factorial, then we have k to the k. So k to the k is the fastest. So here, denominator, if denominator grow faster, what do you get? Denominator get bigger, 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 and then this guy is 0. If numerator go faster, the ratio, the quotient is gonna be infinity. But if the denominator grow faster, the quotient is gonna be 0. Has the limit 0. Okay. Oh, 0. 0 means I need to go to the second step, right? Divergence test tells us nothing. So we go to the second steps, and because we say this function looks like an integrable function, so and we define f, and we say it's continuous, positive, and decreasing. And it is, see, let's look at the picture, it's continuous, positive, and decreasing. All right, and then we can compute the integral. So we replace the improper value to be t. Then we can do u substitution, right? We say, oh, this is our u, and then this is like our du, right? Because derivative of ln of x is 1 over x du. So, yeah, 1 over x, yes, and that is du. Okay, so what is that? So this guy is the same as integral of u du. Integral of u du is you add 1 to the exponent, u squared over 2. But evaluate from, this is x1, and this is x equals to t. Okay, so we plug in t minus we plug in 1. So this is what we get. All right, so we plug it in, and let's see what happened. When t goes to infinity, this guy just goes to infinity. So this guy is infinity. Wow. So it means the integral diverges. So we say by integral test, our series also diverges. Okay, so that's part D. And we still have one last one. Okay, so yeah, for all of these problems, I hope that you can pause the video and then try it by yourself first. Okay, so this is actually very similar to what we have done before, right? You remember the first step, you always compute the limits of the sequence. And don't forget to write the limits. And you know, constant over something goes to infinity. That is 0. 0 means go to the next steps. Okay? So next steps, you can see k downstairs. So it's like 1 over k. So the derivative of ln of k is 1 over k. So that's why this guy is an integrable function. We define f of x to be 6x ln of x to the 8 over 3. And we say this guy is continuous, positive, and decreasing. Integral from 2 to infinity of this guy. Alright, so we replace the improper value by t, and we let t goes to infinity. So here, same u substitution. Okay, so this is our u, and then du will be 1 over x dx. My u looks so du. Okay. All right. So this guy is like a 6. We can move the 6 outside, and then we have like u to the negative 8 over 3 du. And those are u values. Oops, this should be t. So this is u of t. Okay? Yeah, so this is different notation. You can say u of 2, u of t, or you can say x equals to 2, x equals to t. So either ways works. We means those are the x values. Those are not the u values. Okay, so don't plug the x values into the u, or don't plug the u values into the x. Okay, so we integrate. We get add 1 to the exponents, becomes minus 5/3. Okay, so minus 5/3, and then over minus 5 times 3. All right, and then we evaluate from u to u of t. So that equals, okay, so 3 times 6 is 18. And the u is negative, so sorry, the exponent is negative. It means it leaves in the denominator. Okay, now we get the x back. We can plug in 2 and t. We plug in t first. And minus minus become plus. We plug in 2. Okay, what happened when t goes to infinity? See, the first term, our denominator goes to infinity, so this guy goes to 0. So our answer is 18 over 5. ln of 2, and then to the 5 over 3. So far, so good, everybody? Okay, so we get a number, so it converges. So by integral test, our series also converges. Okay, so that finished the problem. Okay, you can see example part D and E are actually quite similar, but one of them, the integral and the series diverges. And the other one, we have the integral and the series converges. That is because after you integrate, does your u lives in the numerator or in the denominator? If the u lives in the numerator, when u goes to infinity, then it just become infinity. But when the u goes to the denominator, when t goes to infinity, then the u will go this whole thing, the whole term will go to 0. Okay. All right, so that is 8.4. Feel free to print screen and ask me questions. Bye.